Assalamualaikum warahmatullahi wabarakatuh. Shalom, Om Swastiastu, Namo Buddhaya, Salam Kebajikan. Hello everyone, introducing my name is Berbi Lovina with the last three digit of my student number is 098. Previously, I thank Mr. Dr. Heri Septiakusuma SSCMT as the lecturer in the physical chemistry course for the opportunity that have been given. I made this video in order to fulfill the end of semester evaluation. The topic I broke up was thermal equilibrium with the title Integrated Thermal Equilibrium Tank Reactor for Efficient Treatment of Industrial Waste. This material will be divided into several chapters, namely first, Introduction, Technological Revolution in the Waste Treatment and Temperature Management, ITER Design and Technology, Advantage and Application of ITER, ITER Challenge and Implementation, ITER Comparison and Impact Analysis, and the last, Conclusion and Suggestion. First chapter is Introduction. What's the problem? So, industrial waste treatment has become a major challenge for various sectors such as manufacturing, energy, and chemical in the recent decade. Waste generated by various industries often contain dangerous material, are difficult to decompose, or difficult to manage with conventional methods. Such waste not only pollute the environment but also risks reducing operation efficiency. For, for example, organic and plastic waste that are difficult to decompose of the hinder sustainable environmental management and can cause long-term damage. Therefore, more efficient and sustainable waste treatment technology are required to reduce environmental impact and meet sustainability standard. Many industries have begun to turn to more environmentally friendly waste treatment technologies such as pyrolysis, gasification, and hydrolysis. While these technologies often solution for treating industrial waste, they are also face several challenges, one of which is temperature imbalance in the reactor that affect the efficiency and safety of the process. Temperature imbalance that occurs in the reactor system can result in significant energy waste and potential failures in the reactor, ultimately hindering the widespread development of these technologies. As I said earlier, one of the main problems often encountered in industrial waste treatment is temperature imbalance in chemical reactor. Thermal equilibrium or an even distribution of temperature throughout the reactor system is essential to ensure that chemical reaction can process efficiently and safely. Temperature imbalance often lead to localized hotspot. This can affect for this can affect reactor performance in several detrimental ways. This imbalance not only worsen process efficiency but also increase the risk of harmful byproduct formation and lower the selectivity of the desired reaction. Some of the effects of thermal imbalance are catalysts. The first catalyst degradation and reduce reaction selectivity. Catalysts used in reactors, such as in pyrolysis or gasification process, are very sensitive to temperature fluctuation. Temperature imbalance can damage the catalyst, reduce reaction efficiency, and produce when byproducts such as solid carbon or harmful gases. This can reduce the yield of the desired main product and add operation costs for maintenance or catalyst replacement. And two, significant energy loss. Temperature and unstable reactor require more energy to maintain the optimal temperature for the reaction. Inefficient heat transfer process also lead to energy waste. This is particularly problematic in processes that require sustained high temperatures, such as pyrolysis and gasification of waste plastic or biomass. This energy wasted increase operation costs and can affect the competitiveness of the industry in the long run. And three, process failure and safety risks. So temperature imbalance can cause a serious problem in waste treatment that require extreme temperature. When temperatures are poorly controlled, the risk of system failure increases, which can lead to industrial accident or fires. Waste treatment process such as gasification or pyrolysis have the potential to produce dangerous reaction that require very strict temperature control. Therefore, improper temperature management can reduce the level of occupation safety and increase the potential for material and environmental loss. So, what's the solution for this reason? A solution is needed that can not only maintain a sustainable temperature in the reactor, but also improve thermal efficiency and overall safety. The integrated thermal equilibrium tank reactor is an innovative solution designed to solve this problem. ITER combines smart material technology, IoT-based sensor, and thermal nanofluid to achieve thermal equilibrium actively and dynamically throughout the process. This system enables even heat distribution throughout the reactor tank, reducing the risk of hotspot, improving energy efficiency, and extending catalyst life. In addition, ATER is also designed to adapt to various types of industrial process for plastic waste treatment to biomass, making it a flexible solution for waste treatment in various industrial sectors. By utilizing the concept of thermal equilibrium, ITER has the potential to revolutionize industrial waste treatment and um, introduce more sustainable and efficient process in reducing the environmental impact of industrial waste. The approach is not only relevant for a conventional chemical process but also for renewable energy application and the processing of temperature sensitive chemical. ITER enable waste treatment with a lower impact on the environmental whilst providing higher energy efficiency, which is key for the sustainability-oriented industries. Okay, next, the second chapter is technological revolution in waste treatment and temperature management. Industrial waste treatment. Industrial waste treatment is an important process in maintaining environmental sustainability and preventing ecosystem pollution. Industrial waste can be categorized as solid, liquid, and gaseous waste generated for various sectors such as manufacturing, textile, plastic, and biomass. Along with industrial development, waste treatment technology continue to evolve to improve process efficiency and reduce negative impact on the environmental. Industrial waste treatment. Industrial waste treatment Industrial waste treatment. Industrial waste treatment is an important process in the maintaining environmental sustainability and preventing ecosystem pollution. Industrial waste can be categorized as liquid, solid, and gaseous waste generated from various sectors such as manufacturing, technology, plastic, and biomass. Along with industrial development, waste treatment technology continue to evolve to improve process efficiency and reduce negative impact on the environmental. The main waste treatment technology used involve pyrolysis, gasification, and hydrolysis. Major waste treatment technology. But the first, pyrolysis. Pyrolysis is the process of breaking down organic material at a high temperature in the absence of oxygen, which produce products such as synthetic gas, pyrolysis oil, and solid carbon residue. This technology is effective in treatment plastic and biomass waste and has the potential to support the circular economy by converting waste into a valuable product. And two, gasification, on the other hand, is the process of converting biomass or other organic material into synthetic gas or syngas, which can be used for energy generation. This process requires high temperature and tight thermal control to achieve optimal conversion efficiency. And three, hydrolysis. Hydrolysis is the breakdown of organic material using water under control condition and temperature and pressure. One example of the application of hydrolysis is enzymatic hydrolysis, which has been proven effective for recycling or pyrolysis plastic, which the increasing complexity of the type of industrial waste produce innovative technology that are more efficient and environmentally friendly are needed so that the waste treatment process can maximally support the goals of industrial sustainability. Okay. Next, thermal equilibrium in chemical reactor. Thermal equilibrium in chemical reactor is that in which the temperature distribution throughout the reactor system is uniform. Temperature imbalance, which often result in hotspot, can cause some major problems such as energy wastage, catalyst degradation, and formation of unwanted byproduct. Energy waste occurs when temperature imbalance results in inefficient use of energy to maintaining the optimal temperature in the reaction process. Catalyst degradation, especially temperature-sensitive catalysts, can impair reactor performance, decrease reaction efficiency, and increase maintenance costs. In addition, thermal imbalance can increase the risk of dangerous byproduct formation, such as solid carbon or toxic gases. To address this challenge, smart material technology and sensor-based temperature control systems have been developed. Smart materials such as fast-change material or PCMs are able to absorb and release heat efficiently, maintaining temperature stability in the reactor, while sensor-based temperature control systems allow for more even heat distribution, improving efficiency and temperature stability in chemical reactor. And three, advanced reactor technology. And for reactor design now incorporate various technology innovation and improve thermal efficiency and overall reactor performance. One of them is the use of patching material or PCM, which can store and release heat at the specific temperature, serving as a natural temperature regulation in the reactor, thereby improving thermal stability. In addition, phononic metamaterial technology is used to optimize heat distribution through material engineering. Phononic metamaterials enable efficient movement of heat within the reactor, which contributes to better and more efficient temperature regulation. The use of thermal nanofluid or nanofluid enriched with metal nanoparticle has also been shown to improve thermal condition and heat transfer efficiency in reactor system. Recent studies have shown that the use of nanofluid can increase thermal efficiency by up to 20% compared to a conventional fluid. In addition, the integration of the Internet of Things or IoT and artificial intelligence in the reactor system enable real-time temperature monitoring and highly precisely automatic control. The system can accurately detect temperature imbalance and dynamically optimize reactor operation parameter, resulting in more efficient and environmental friendly process. And next, innovation in waste treatment with ITER. The integrated thermal equilibrium reactor offers an innovative solution to address industrial waste treatment challenge by maintaining optimal temperature stability inside the reactor. ITER technology integrates advanced temperature control system using various technologies such as smart material or PCM and IoT-based sensor for real-time temperature monitoring and the thermal nanofluid to improve heat condition in the reactor. I mean, and thermal nanofluid to improve heat conductivity in the reactor. In pyrolysis gasification and pyrolysis process, ITER offer several significant advantages. These include even temperature distribution and produce high quality product by minimizing the formation of harmful byproduct. With this innovation, ITER has the potential to reduce the environmental impact of industrial waste and help support industrial sustainability through more efficient and environmentally friendly process. Okay, the next chapter is ITER design and technology. The first basic concept of ITER. ITER is a technology developed to address the challenge of temperature imbalance in chemical reactor, which often hammer process efficiency. ITER works to keep the temperature in the reactor uniform and stable, which is an important factor in involving the efficiency of industrial waste treatment. To achieve this, ITER incorporate a variety of advantage components, including phase change material or PCM, aero, aero, aerogel, and thermal nanofluid. PCM plays a role in absorbing and releasing heat as the material undergoes a phase change, which enable temperature stabilization in the reactor. Meanwhile, aerogel are used for thermal insulation, reducing heat loss and improving heat distribution efficiency in the reactor system. Thermal nanofluid, which is a mixture of nanofluid improve thermal conductivity and accelerate heat transfer, which is improve thermal conductivity and accelerate the heat transfer process, allowing the system to work more efficiently. In addition, ITER is equipped with the IoT and AI-based control system, which monitoring and regulate temperature in the real time for maximum efficiency in every waste treatment process. Okay, the next main components of ITER. First, the first phase change material or PCM. PCM are used in ITER to absorb or release heat at specific temperature, which help keep the temperature stable in the reactor. While this material changes phase either from solid to liquid or vice versa, thermal energy is absorbed or released, allowing the temperature stabilization in the system. Proper selection of the PCM is critical to the effectiveness of this system, as it must have a high energy storage capacity and can pass at the temperatures sustainable suitable for the process being carried out. And the next, aerogel-based insulating material and phonic metal material. Aerogel are known as material with excellent thermal engulfing, which are used in ITER to reduce heat loss and improve heat distribution efficiency in the reactor. With very low thermal conductivity, aerogel help keep the internal temperature of the reactor stable and controlled. Meanwhile, phononic metamaterial, which are material designed to control the movement of heat waves, serve to optimize heat distribution, which the temperature, maximizing the use of available energy. And thermal nanofluid for heat transfer. Thermal nanofluid in ITER contain metals nanoparticles that are added to the fluid, increasing its thermal conductivity. The use of thermal nanofluid allows for increased heat transfer efficiency in the reactor system. Recent research has known that the use of nanofluid in chemical reactor can increase thermal efficiency by up to 20% compared to conventional fluid. And the last, IoT and AI-based control system. IoT and AI technology can play an important role in controlling the temperature in ITER. The system enables real-time temperature monitoring and automatic control, which allow for more precise temperature regulation in the reactor process. Using IoT sensor, the system can detect temperature imbalance with high precision and dynamic adjust reactor operating parameter. So improving efficiency and reducing energy waste. And three, ITER operation process. ITER can be applied in the various industrial waste treatment process such as pyrolysis, gasification, and hydrolysis. Pyrolysis in the pyrolysis process, ITER maintaining a stable temperature during the heating of organic materials such as waste, plastic, or biomass to product such as synthetic gas and pyrolysis oil. This process requires strict temperature control to ensure that the material degrades efficiently and produce a flammable product. And two, gasification. So gasification is the process of converting biomass into synthetic gas or syngas that can be used to produce energy. ITER ensure even heat distribution in this process, which is essential for converting biomass into useful gas. ITER temperature control system enable high efficiency biomass processing, reducing harmful gas emission, and the last hydrolysis. So in the hydrolysis process, ITER maintaining an optimal temperature to break down organic material into more useful product. The organic process, which is often used to treat plastic-based waste or the organic material, can be performed for efficiency, which praises temperature control, reducing the energy required to keep the desired material degradation. And fourth, equation relating to industrial waste treatment using advantage reactor technology. Okay, so in industrial waste treatment using advantage reactor technology, several physical and chemical formula can be applied to ensure the efficiency and sustainability of the process. One of these is various law for head condition, which is describe the flow of head rock material in the reactor. This formula explains how head flows based on temperature difference, material conductivity, and material thickness, which is critical in temperature management in reactor for process such as pyrolysis and gasification. The formula is Q equal minus Q times A times dt divided dx. So Q is head flow rate. It indicates how much head flow through the material per unit time. And K is thermal conductivity of the material, indicate the ability of the material to conduct heat. Minus sign in this indicate the direction of heat flow, namely from hotter areas to colder areas. And A, the surface area exposed to heat flow determines how much area is used to produce heat. And the last, dt divided dx, are temperature gradients. The change in temperature per unit length allow the material. And the next formula is And the next, the pyrolysis and gasification process itself can be analyzed by an energy equal that describe the energy change in the system during the reaction to optimize energy consumption and avoid waste. The formula is delta E equal Q minus W. Delta E is change in energy in the system. Measure the total change in energy in the reactor system, and K is energy added to the system in the form of heat or energy transferred to the system, and W is work done by the system, the energy used to do mechanical work, for example by an engine or a pump in a reactor. In addition, in gasification process, the ideal gas law can be used to understand the relationship between pressure, volume, temperature, and the number of mole of gas performed during the process. This allows optimization of gas producing from biomass or other organic waste. The formula is E times V equal N times R times T. The P is gas pressure, the force per unit area expressed by a gas on the walls of its container. And V is gas volume, the space occupied by gas in the reactor. N is number of mole of gas, indicate the number of particle in the gas. And R is ideal gas constant constant that relates the energy, temperature, and volume of a gas. And T is gas temperature, so the temperature of the gas in the reactor which affect the behavior of the gas. So the next, chemical reaction rate. So chemical reaction rate are also important to describe how quickly organic matters can be converted to the desired product. Reaction speed depends on the concentration of reactant and temperature, which are regulated in the reactor designed to maximize efficiency. So the formula is R equal K times concentration of A to the n power. So R is reaction rate, indicate the speed of change in the concentration of reactant in chemical reaction, and K is reaction rate constant, describe how fast a reaction occurs at a given temperature, and concentration of A is concentration of reactant A, the number of mole per volume of reactant solution in the system, and N is order of reaction, which is an exponent that show the relationship between the concentration of reactant and the reaction rate. And the last, mm, in enzymatic hydrolysis process, which is used to recycling polyester plastic, mass transfer equation can be used to model how chemicals such as water or enzymes move through the medium in the reactor. This mass flux play can uh, this mass flux play an important role in determining the efficiency of the process and the speed of con- conversion of waste material into more useful product. All of these formula work together to improve the efficiency and effectiveness of the sewage treatment process, while managing energy usage and temperature in the reactor. The formula is G equal minus D times dc divided dx. G is mass flux, which is the rate of mass flow through a unit area per unit times, and D is diffusion coefficient, show how fast a substance moves or spread in a medium, and dc divided dx is concentration gradient, which is change in concentration of a substance per unit length in the director of flow. The chapter 4 is advantage in an application of ITER. The first advantage of ITER in industrial waste treatment. So ITER, or integrated thermal equilibrium reactor, has a number of advantages that make it a revolutionary technology in industrial waste treatment. Some of the key advantages of ITER including one, energy efficiency. Okay, ITER is designed to reduce energy waste by keeping the temperature in the reactor stable and even. With better temperature distribution, the system optimizes energy conversion, making the waste treatment process more efficient overall. And two, by product producing. One of the major challenges in industrial waste treatment is the formation of unweighed byproduct. ITER helps address this issue by precisely regulation the temperature, thereby reducing the formation of toxic gases or other dangerous dangerous waste, as well as increasing the quality of the main product produced. And three, catalyst durability. Stable temperature in the ITR reactor can extend the life of the catalyst, which serves to accelerate chemical reaction which degrade it. Better catalyst durability improve reaction efficiency and reduce the need for period catalyst replacement, which in turn reduce operation cost and waste. In the last, sustainability, ITER support greener waste treatment by producing carbon emission and the amount of waste generated. It contributes to a more sustainable industry by minimizing environmental impact through the reactor of energy recovery and improvement energy conversion efficiency. Yeah, and 4.2 ITER application in forest industry. So ITER can be applied in forest industry sector, providing more efficient and environmentally friendly solution. Some of ITER's main application include first is plastic waste processing industry or pyrolysis. So IT in the plastic pyrolysis process, ITER maintaining the optimal temperature for the decomposition of plastic into higher quality products such as synthetic gas and processed oil. With more efficient temperature distribution, ITER produce energy wells and product prefer unwind byproduct. And the second, biomass specification for energy production. ITER is used in biomass gasification, a process that converts biomass into synthetic gas or syngas, which can be used to produce renewable energy, which is process temperature control system. So ITER can improve the efficiency of renewable energy production by reducing energy waste and greenhouse gas emission. And third, gasification reaction in organic waste treatment. HER is also applied by enzymatic hydrolysis process to treat organic waste in process, which involve the breakdown of organic matters using water under controlled temperature condition can break down complex material in waste into more useful products such as biogas or alternative fuels. And the last is thermal energy storage. So ITER can be used for thermal energy storage, which can support the integration of renewable energy in the energy grid. With its ability to absorb the release heat efficiency, ITER helps increase the flexibility and stability of renewable energy system. And 4.3 case study and trial result. The case study that have been products show that the implementation ITER on a laboratory and industrial scale has shown significant results in improving the efficiency of waste treatment and reducing energy waste. For example, in the chemical industry, ITER has been shown to product energy use by up to 30. So 4.3 case study and trial result. The case study and have been conduct show that the implementation of ITER on laboratory and industrial scale has shown significant result in improving the efficiency of waste treatment and reducing energy waste. For example, the in the chemical industry, ITER has been shown to project energy use by up to 30% compared to conventional technology. Trials conduct in the renewable energy sector have also shown that ITER improve energy conversion efficiency by up to 25% while producing prefer harmful byproduct. These results demonstrate ITER's great potential in transforming the waste industry, treat waste, and manage energy, making it a highly relevant technology to support industrial sustainability and environmental impact production. Chapter 5 is ITER challenge and implementation. 5.1 Challenge in ITER implementation. While ITER offers great benefit, its implementation faces some major challenges. One of them is the cost of the advanced material needed to build ITER, such as superconductor well, which are very expensive. This lead to high construction and operation costs. Another challenge is the complexity of the system that need to be integrated with existing industrial process. The complex system in ITER must be designed to be compatible with existing infrastructure, which requires careful engineering and special attention to reliability and efficiency. In addition, ITR also requires further research to test and validate the performance under real industry conditions, especially to test the durability of the material and their effectiveness in the waste treatment. And 5.0 is strategies to overcome challenge. To overcome this challenge, several strategies are required. So, research to develop more affordable and efficient material is crucial to reduce the cost of manufacturing ITCR without compromising quality or performance. In addition, collaboration between industry and research institution is necessary to accelerate the application of ITER on an industry scale. This collaboration will ensure that ITER can be adopted more quickly with more practical and affordable solutions. In addition, close tests and validation are needed to ensure that ITER can operate properly under real industrial conditions and to identify the area that can be improved to increase efficiency. And 5.3 Future of ITR in Industry. The future of ITR is bright, especially with its potential to be applied in various industry sectors. HER has great potential for more efficient waste treatment and renewable energy storage. It will also play an important role in supporting industrial sustainability by reducing carbon emission and improving energy efficiency. In the long run, ITR could be the ICER could be the technology that changed the way industry manage energy and waste, resulting in a more sustainable and environmentally friendly industry. Chapter 6 is ITR comparison and impact analysis. 6.1 Comparison of ITER with conventional technology. So the first, from energy efficiency aspect, ITER demonstrate higher energy efficiency than conventional energies. In the process of treating industrial waste, ITER can maintaining a stable and even temperature in the reactor, which allow for more optimal energy conversion. This is in contrast to conventional technology that often face energy waste due to uncontrolled temperature fluctuation. The second, and operating cost aspect. So although the initial cost of implement if implementing ITER is higher, the technology has advantage in the long run. With higher energy efficient and better catalyst durability, operation costs can be reduced. ITER reduces the need for period catalyst replacement, which reduce maintaining and operating cost compared to conventional system. And the last, environmental impact aspect. So ITER has a lower environmental impact than conventional technology. It reduces carbon emission and dangerous waste generated during the treatment process, making it a greener option. Meanwhile, many conventional technology produce more waste and emission that pollute the environmental. 6.2 ITR's potential to support a circular economy. For the first transformation of waste into valuable product, ITER provide great potential in transforming waste into high value product with high energy conversion efficiency and production of unwind by product. Industrial waste can be transformed into useful raw material or renewable energy. And next, reduce dependence on new nature resources. ITER technology contributes to the reduction of dependence on new natural research by maximizing the utilization of waste and resources. By using waste as feedstock, ITERs help reduce the exploitation of increasingly limited new natural resources. And the last, recycling waste into energy and raw material. So ITER support the recycling of waste into energy and raw material with the ability to process waste into synthetic gas, biogas, or alternative fuel. ITER provide a sustainable solution in support of a circular economy where a waste is processed into reusable product. 6.3 Economic and environmental impact case study. Case study 1 is application of ITER in plastic waste pyrolysis industry. The increased yield of high quality product. So in the application of ITER to the plastic pyrolysis process, ITER maintaining an optimal temperature that enables the decomposition of plastic into higher quality products, such as synthetic gas and pyrolysis oil. This product has a higher selling value and better quality compared to the product produced by conventional process. And to reduce gas emission. So ITR reduce exhaust emission by ensuring the pyrolysis process takes place at a controlled temperature, avoiding the formation of toxic gases and reducing the air pollution generated during the process. So this make it a more environmentally friendly solution. And the last analysis of economic benefit over 5 years. The economic study showed that within a 5-year period, the application of ITER in the plastic pyrolysis industry can reduce operating costs by 25% and increase profit by producing more valuable high quality product. And I study too ITER on biomass gasification. So ITER comprises efficiency aspect. ITER application to biomass gasification, the energy involved, the conversion efficiency to biomass into synthetic gas or syngas, which is used to produce renewable energy. A more efficient process product energy wastage and increase renewable energy yield. And increase energy reliable energy sustainability. ITER also contribute to renewable energy sustainability by producing greenhouse gas emission products during biomass gasification, which presses technology control. ITER optimize this process to product cleaner and more efficient renewable energy. And the next chapter is conclusion and suggestion. So the conclusion of this this topic that industrial waste. Okay, the last chapter is conclusion and suggestion. So the conclusion of this topic is that industrial waste treatment requires advantage and environmentally friendly technology. ITER or integrated thermal equilibrium reactor emerges as a solution by maintaining stable temperature inside the reactor, improving energy efficiency, reducing waste, and producing quality product while reducing environmental impact. ICER can be applied in waste plastic treatment, biomass gasification, and organic waste hydrolysis. Disparate cost and integration challenge with existing system. ITER has the potential to reduce long-term operation costs and environmental impact compared to conventional technology. ITER support a circular economy by converting waste into high-value product, reducing dependence on the natural resource, and recycling waste into energy or feedstock. Case studies show that ICER can improve efficiency, reducing emission, and provide efficient economic and environmental benefit. Conservation future research is needed to develop ITER at a more affordable cost and increase its application on an industrial scale. Collaboration between industry and research institution is also very important to accelerate the implementation of ITER in the wider industry. So this is the reference that I use. Okay, so many reference. Okay, I can't believe we reset at the end of the discussion. I will Lovina. Apologies if there are any shortcomings in my explanation. So, wassalamualaikum warahmatullahi wabarakatuh. Thank you, everyone.